Welcome to Center of Math's basic series on field theory. Today we're going to talk about extensions. So say we have two fields F and K. F is contained in K, so K we say is a finite extension, field extension of F. If K is a finite dimensional vector space over F, so it has some elements x1, x2, xn, has dimension n, and we can take scalars in F, and any element in K can be represented that way. And so the dimension of this vector space is the degree of the field extension, degree K dot colon F. So one thing we can prove is if we have two finite extensions, so we're going to say E is a finite field extension of F, some field F, and we have another extension K is some finite field extension of E, then we can show K is in fact a finite field extension of F, and the degree of K over F is equal to the degree of K over E times degree of E over F. So we're going to take we have some base A1 to AM for E over F, some base B1 to Bn for K over E. So any element K in our field K, we can represent K as some sum with elements xj in E and some other elements bj, since K is a finite dimensional vector space over E. And same thing for any element xj and E. E is a finite dimensional vector space over F, so we can represent that with the AIs times some elements in F. So plugging in the xj's to our expression for our arbitrary elements from K, we get K equals some double sum of elements Yij, AI. Yeah, elements Yij times AI Bj, and this shows that so Yij is all in F, AI Bj, these elements in fact all these elements form our spanning set for our vector space, for our space K over F. So these AI Bj's are a spanning set. So we just need to make sure that these are in fact independent. So if we say we have sum over Yij's with AI Bj's equals 0, so we know we can put this in parentheses, that this is the scalars in front of the Bj's. So because all the elements, all these elements Bj are a base for a vector space, so they are linearly independent. So these scalar coefficients must all be 0 for this to equal 0. So these are all 0, but then the AIs are also independent, so we have all the Yij's must equal 0 in this case, and so the AIs, Bj's are a linearly independent spanning set. They're also independent, so they are a base for a vector space, and this proves our theorem. So another thing we can prove, if we have some element A and an extension K of F, and A is a root of some polynomial over the ring of polynomials in indeterminate X, and is a root of this polynomial is irreducible and of degree n, then the extension of F, the smallest field containing F and A over F, is of degree n of the irreducible polynomial. So first, we note that the smallest field containing f and a is spanned by the elements 1, a squared, etc., all the non-negative powers of a. You can check this by using the fact that since a is spanned by, since a is the zero of some irreducible polynomial, if you divide by some powers of a's, you can always multiply the bomb by some polynomial to make the bomb equal 1. And then you'll get back, it's just going to be powers of a. So we can write, so this is the same as it's spanned by all the polynomials p of x in the field, the ring of polynomials with coefficients in f over indeterminate x. And you're just plugging in a into those polynomials. So that'll give you all the elements of our field. So we can write p of x as q of x times f of x plus r of x. F of x is the irreducible polynomial. R of x is some remainder of degree less than f of x. So r of x has degree at most n minus 1. And so from this we see 1, a, n minus 1 must in fact span our field. Since if we plug in a to both sides, p of a equals r of a. R of a takes the highest power in R of A is as most n minus 1. So this is the spanning set. So now we just need to know that these are linearly independent. And they're linearly independent since otherwise we would have a polynomial, some polynomial p of x of degree less than f of x, which also has a factor of a, or p of a equals 0. But this would contradict f of x being the irreducible polynomial with a root of a. And so these must be linearly independent. Thanks for watching. Please check out centermath.org, check out our blog, and follow us on Facebook and Twitter. Thank you.